Thanks a lot and good afternoon. So my name is Pablo and I'm here to talk to you about the co-implementation of DNS load balancing at CERN. My talk is going to be divided in two parts. The first thing, I'm going to talk a little bit about CERN. I mean, it's the place where I work, it's the place that I like a lot, and I want to share all of the things that we are doing there with you. Then I will go more into the DNS load balancing and what we have done in the recent year with that. Finally, a bit of the things that I plan to do. That slide has changed quite a lot in the last 24 hours after some of the talks that I've seen here, because I've seen that I have to learn a lot of things about Go. Yeah. Okay, so let's start, oops, not from the beginning, from the next slide. CERN. So the European Center for Particle Physics, it was founded almost 65 years ago, so we are almost 65. And at the moment, we have 22 member states, most of them within Europe. Of course, Switzerland is there, France is there, Italy is there, Spain is there. We have all of those countries. There are another 3 countries, Cyprus, Serbia, and Slovenia, who are in the process of also becoming member states. There are also other countries or even some associations that they do not participate actively, so they don't participate, they don't have a vote in what we do. They do participate sending people or even money or even some of the projects. And in those ones we include the United States, Russia, well, the European Union and things like that. I have a problem with this one, yes. So on the campus we have like 2,000 people working for CERN and quite a lot of students. And we have also a lot of people who work with us remotely or that come to us for a couple of months, and then they go back to their home institute and they continue working from there. So in total, we have around 11,000 people working all over, from all over the world. And our budget is like 1 billion Swiss francs per year. CERN is very well known for physics, of course. That's our main thing, the thing that we do. We do particle physics or fundamental research, or the way that I usually put it, investigating just for the fun of it, doing things that we don't know what's going to come out of it. And the nice thing is that a lot of times we get some things from it. In particular, the World Wide Web, it was born at CERN, and we like bragging about that. CERN is also quite well known for being in the media, so there's this movie of Angels and Demons. Have you seen it? Yeah. Quite nice, so it features CERN. The Big Bang Theory, they talk about us quite often also. And I remember when my sister-in-law showed the first episode, she watched the first season back to back, all the episodes, and then she called my wife, "Hey, I've just seen a show about your husband and his friends." And yes, I don't know which of the characters I am, but well. Then there are also some flash forwards and daily show. They have a very nice episode about CERN. And before moving to the next slides, I want to apologize in advance. I'm going to brag a little bit about CERN, because the largest machine at CERN in the world is located at CERN, so 600 kilometers from here to the north, and you can see it on this picture over here. To get an idea of the scale, this thing here is the airport of Geneva. On the left, we see the lake, and the big circle is the Large Hadron Collider. So it's a machine of 27 kilometers that is buried like 100 meters underground. The machine is in the border, or it crosses the border multiple times between Switzerland on the right-hand side, France on the left-hand side. And there are 2 sites of CERN. So we have one campus, also in the border with some part in Switzerland, some part in France, and another one a bit more only on the French territory. And what we do is we take particles, at the moment protons or heavy ions, and we start making them go in circles and accelerating them. At the beginning, we put them on very small circles, like this one accelerator, and once they are fast enough, we send them to the next one. Again, we keep giving them more energy, so accelerating them even more, almost to the speed of light, and then we send them to the last one, to the one of the 27 kilometers that we have mentioned before. And finally, what we do with these things is we are sending them in one direction, we send also in the other direction, and we make them collide, and we see what happens. And we make them collide Yes, we make them collide in 4 different places. So all of these things under control. These places that are 4 big detectors in alphabetical order: alias, atlas, LSTB, and CMS. I like doing them in alphabetical order because I used to work in alias, so I was always starting with my own experiment. So more things that you can know about CERN. We have a lot of magnets. And magnets, we use them a lot for various reasons. We've been talking that we have these particles that we have to accelerate. And it's easy to accelerate them because these particles, they have some charge. And then with a powerful magnet, you can make them go faster and faster every time that they go through them. So in fact, we have 3 different types of magnets at CERN. Ones that they go more energy to the particles, and then they make them go faster. Another one that makes them turn, because otherwise the particles will go on the straight line, and we cannot reuse them. So with this second one, we make them go around in circles. And the third one is that the particles that we use are very, very small. So sending one, it will be very difficult. What we do is to send like a beam of them, a lot of them. And they are so close together that they don't like each other, and they try to get away from each other. And we have a third set of magnets to concentrate them and to focus the beam. The beam is what you see in this particular picture. There are like 2 small lines here in yellow. So those are the 2 beams where the particles will go in the different directions. And inside those beams, that is basically like this size. Sorry, wrong button again. Tick, 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 almost there. Inside those beams is one of the emptiest places of the universe, because we want to make sure that our particles, they collide with the particles that we send in the other direction and not with anything else. So we have to make sure that those particular places are almost as empty. It's like 10 times emptier than the moon and even emptier than most of the known universe. The nice thing of these magnets is that they also need to work in the mode that we want them to work. They have to be very, very, very cold. So almost to the absolute zero. So in fact, it's like 1.9 Kelvin, which is also the coldest place in the known universe. It's colder than the average temperature of the universe, which is at the moment like 2.9, someone told me. I don't know how they measured it, but that's what they told me. And finally, we also have the largest detectors. This one that we see here is a diagram of Atlas to give us an idea of the scale. Those things here are people. So it's like a 5-story building, all underground, so 100 meters underground. And this one weighs more or less the same thing as the Eiffel Tower. And in this one, what we are doing, as I mentioned before, is to I'll get the hang of it at this point. Tick, tick, tick. Yes. So we send the beam in both directions, we make them collide, and then we see all these things that happen here. So when they collide, they produce new particles, and all those new particles, they are recorded in all these detectors. There is a website that I like quite a lot that explains all these things for children. Well, for children and for adults. I think I like this one more than my daughter, because it's also quite, it explains in basic terms. So here you see also all these things and the things that we do. And it's also in 8 different languages, so you can choose the one that you prefer, including Italian. I just want to mention that this is a bit of a simplification. So for instance, here we see, again, the Large Hadron Collider with the different accelerators. In real terms, it's a bit more like this, because we have quite a lot of different accelerators in order to be able to get to that point. The last thing that I want to say, while I'm still on the topic of CERN, is that we are always hiring. So if you are interested in coming to work with us, take a look at our web pages and the human resources, and you will see quite a lot of interesting projects where you can contribute. Okay, so DNS load balancing. This concept, I think, is quite well known. It has been around for quite a lot of time. And the basic idea is that you have one name, and behind that name, multiple machines. This is good for a lot of reasons, because then if you want to scale, you can add more nodes there, and then it will distribute the load. And also, it can be used for high availability. If one of the nodes goes down, you don't really care because all the others are going to do all the work of those things. For the load balancing, there are a lot of options. It can be something static, like a simple round robin that goes host by host, or something a bit more elaborated or dynamic, where you question also how the nodes are behaving and then send the payload accordingly. A very simple example is the website of this conference. If you go there, you can go directly to one node or another. So at CERN, what we have done is we have an alias, and we want to have a lot of nodes behind it. Inside each of these nodes, we embed a single, very simple program that is going to tell us how the node behaves, something that we call the Lbclient. And we also configure something quite basic, SNMPD, to be able to talk to that. Then we have a server that has the configuration of all the aliases and the nodes that are supposed to be behind it. And every so often, from 5 minutes to 15 minutes, however the service manager wants, it will probe all the nodes, asking them if they are healthy or not, and select the healthiest nodes and put those ones behind the alias. So in this particular example, we see that it asks the 4 nodes. One of them, it tells it, hey, I'm only loaded like at 7 points, which happens to be the lowest positive number of all the nodes, and that node will be selected to be behind the alias at that moment. What it does then, the server, is to contact the DNS server through the SOAP interface and plop, put that one there. So if any client all over the world, they want to connect to that particular alias 1, they just have to talk to the DNS. The DNS will give back the node 2, and the node will connect directly to node 2. Quite simple. This has been around for, I think that the first implementation that we had of this was like 14 years ago. What we have done recently is to modify all these things to use Go. In particular, the Lbclient and the server, the GoLBD. And this is what I'm going to mention in my next slides. First, the part of the code that we put on the nodes itself, this GoLBclient, so this box here that you have with the blue thing and the white at the bottom, that it's pretty simple. Basically, it receives a configuration of what it has to check, and then it returns a positive number if it's working properly, a negative number if it's not working, and, well, it does not return if it's not there. The checks that it can do are quite a lot, from checking the disk space that you have on your machine, or checking if a particular service is running or is listening in a particular port. We can also put any collect the metric that you want. And as a matter of fact, the whole thing was less than 2,000 lines of code. We put also like 500 lines of test and 300 lines of the configuration. And something that helped us quite a lot is that for all these things, we could depend quite a lot on the community and import a lot of packages from out there. For the server part, quite similar. So this thing, what it has to do, again, is to read the alias configuration, check which nodes are supposed to be there, and ask them the status of every particular node. The way we have deployed it, the configuration of this particular guy will be created by Puppet. I'll come back to that a bit later in my talk. And in that configuration file, there's something about how the alias has to behave. In particular, how many nodes you want to have behind the alias, or things a bit more elaborated, as what do you want to happen if all the nodes are unhealthy? If you want to keep the latest state, or if you want to keep the alias empty, or things like that. With those things, again, the daemon part is a bit more than 1,000 lines of Go code. In this one, we have to improve on the testing. And we, again, depend quite a lot on the vendoring for the packages. In this one, we also have like a big surprise. I should have started with this. This was our first project in Go. So we are not Go experts. And I'm pretty sure that some of the things that we are doing here, it could be done in a better way. So if you have any suggestions, please let me know, and I'll be very grateful to hear those things. So in this one in particular, so we were going for this Go SNMP library that looked quite similar to what we had before, and it looked like a nice alternative to do it. And we got a bit lost because there were 35 different modules doing the same thing. And it took us a little bit of playing. We took this one, which had most of the things that we wanted, and then we had to add a little bit more. We sent the pull request to merge our changes, and then we are happy with that one there. By the way, all of our code is also on GitHub, so you can get it from there, including other modules. The end of this GoLBD is all these parallel features of Go. Because what we are doing at the end on this program is very, very parallel. You have a set of aliases. In our case, it's around 700. And each alias might have multiple machines behind. It gets a bit more complicated because the same machine could also be behind multiple aliases. So what we do is two loops. The first one, we go through all the hosts that we have and query the status. And then we wait until all of those subroutines finish, and then we go for each of the aliases of the status that we have already retrieved and select the best nodes. And then we update the SNMP. The first thing that we notice is that the running time decreased quite a lot from the sequential execution that we had before, now with this parallel. So from 5 minutes that it used to take us to go through the 700 aliases, now in 1 minute we can do all of those things. The other thing that we noticed, and it's something that Philip also mentioned before, that we have to be careful with the file descriptors. We started with 10, 20, 100 aliases, and everything went fine. At some point, we increased it to 400, and we ran out of file descriptors on the machine, and it crashed. I'll get to that also a bit later on another slide. The third component that we have on the system is a bit more for the persistency of what you want to have. This is a web interface with a database behind that is used to keep how many aliases you want. At the moment, this is done in Django. Yes, I'll have something about that later on as well. And basically, this interface, it has two tasks to do. Whenever we want a new alias, so it does all the operations of creating an alias or reading or updating or deleting from the DNS, and also from the configuration that we have on MySQL. Based on this database is where we are going to create the different configuration files for our LBDs. As I mentioned, this is just an optional component. The structure that we have also given to some of our colleagues in another institutes, and they're running a simplified version without this part. So they have the manual file, the configuration file that they keep manually, and that they are running the LBD on top of that. So from the point of view of the user, when they want to create a new alias, they have to do at the moment two things. The first thing, going to a particular website where they have to say, hey, this is the name of the alias that I want. And then the web page is going to check that the alias is still available and things like that. And they have to give a little bit of the parameters of what they really want, like, for instance, how many hosts they want behind. And on all the nodes that they want to have behind the alias, they have to install the service that we wanted, the Lbclient, and to configure SNMPD to be able to listen to us. We've helped our colleagues providing like a Puppet manifest to do those things. So if they include these things, they will be able to set up those things automatically. Let me go a bit more into this database, because we use it also for other cases. Basically, so now we have this Hermes component, a database with a web interface on front, where we keep a list of all the aliases that we want, how often we want to query the nodes behind the alias, and something that we introduced recently of the partition. This is quite nice because it allows us to decouple what is in production and what is in development. So you can play with some of the things while you have your services running there. This is because you don't want to introduce here new services and break all the things. I will get a lot of calls from unhappy service managers. With this, what we do is we have 2 instances of the load balance daemon, each one running on different aliases and on different configuration files, and on different things that we will have to do at the end of the day. For high availability, we also have a second set of LBDs on each of the partitions that they do almost all the things that the other one does. So in fact, they also query all the nodes and check how healthy they are. It does not update the DNS. What it does is only query the master one to see if the master one is still alive. If the master one is not alive, then it will start also updating the DNS. The reason behind it is that you don't want 2 different things updating the DNS and changing each other all the time. So it's better that they can monitor each other, and the slave does that. So it checks if the other one is up. If it's up, okay, it steps back. If it's not, then it goes forward and it does all the updates to the DNS. Then, what we have also worked is on being able to integrate all of that in our module and to deploy it in an easier way. So we have the continuous integration of both the GoLBD and the Lbclient with GitLab. We have different steps. The first one to build the package that we used to do with the GoDep restore. I think that we will have to change that in the near future. We were also testing that the things were working properly, including also with the race condition. This is something that we also painfully learned that could be an issue here. Once those things are working, what we also do is to create a source RPM that is what contains the module, and it will be deployed either on the client or on the service. The small trick here is that, so we create the source RPM still within GitLab, where we have access all to the outside, and then we give all this source RPM with all the vendoring to another service, Koji, that, at least in our case, it does not have any contact to the outside. And that's why we have to package everything, send it there, it will create the RPM, and then that RPM gets installed wherever we want it. The nice thing of all of this is that it's integrated, so from development to deployment is quite easy. Here we have like a snapshot of our GitLab integration. Whenever we do a commit, we will see all these things. I choose to take the snapshot in a moment when everything was working so that it looks greenish. Sometimes it doesn't look like this. We see all these green ticks. The first 4 that we see in the bottom 3 workflows are the ones that I mentioned before of go build, go test, source RPM, and create an RPM. And those things are done every time that there's a commit, a push to the repository. On the top one, which is slightly different, we see that there are also more stages. This is done only whenever we tag the code. And then we have the first 4 ones that are identical, and this thing of tag QA and tag production, so that we say that this RPM is good enough, let's put it on more machines and see how it works. And if that still works, 1 week later, we will also put it in production. The next thing that we have is also a lot of monitoring of all these things, of how it behaves. This, at the moment, we have with the Logstars, Elasticsearch, and Kibana. So this is reading the log files of our service and publishing in Elasticsearch, and then we create some graphs like this where we can see how many aliases we have, how many nodes we have, and the log files of all our services. So that whenever we see an error in any of those machines, it will go to a centralized place. So this is the dashboard where we can control how our machines are behaving. Let's go back a little bit of what we have learned about Go. And the first thing is that all these things of Go and the subroutines and the parallelisms is great. That helped us a lot. It has simplified our life. It makes our program goes faster, and we are really happy about that. The strict compilation is also quite nice, and it helps finding a lot of the problems already at compilation time, which is quite nice. And that there are a lot of packages already out there that you can get and use, and if you can even contribute upstream. So this is something that we really believe on. The next bullet, I have it because one of our developers comes from a Java environment, and the poor guy spent like the first 3 weeks pulling his hair that he didn't have like an object class, something that will affect for all those things. Well, he doesn't pull his hair anymore. He's bald. I think that he has got around to doing this in a different way. And the other thing is that we found out, but maybe it's because we were doing this thing wrong, we were using a lot of interfaces and reflection to see what type of things we were reading, and that the reflection is very, very expensive. So probably there's a better way of doing that. There is one also, this one was quite painful. These 4 lines of code. So basically what we have is the name of a machine, and we want to get all the IPs that are behind it. They might be IPv4, they might be IPv6, and this to us, it looked quite straightforward. So I have a host, give me all the IPs, and if there's an error, I will deal with that. So in this particular one, at least I put a print statement in the file, and at least I will be aware of that happening. What happened is that we were never getting to this part of the code, and we didn't know what. At the beginning, it was normal because we didn't have that many aliases, and things were looking fine. At some point, we were increasing the number of aliases, and we did detect some strange behavior. Like sometimes an alias will only have machines with IPv6 addresses behind, which was a problem because some of the clients will not be able to connect. What we learned is that we have to read the documentation very, very carefully, because this one in particular, it says that this net lookup IP, it might fail, and if it fails in the middle, it might return partial results, which was quite bad for us, because either we wanted it to fail so that we don't have the machine, or if it works, at least to have all the IPs behind it. And then the way to solve it, it was also quite easy. Once we knew that, just put this thing that I want, if there's a partial error, yeah, give me an error. I don't want to have only a partial result. Okay, with this, I get to my future plans. A lot of these things have been added now. So I learned that what we have at the moment is not a production service, it's just a draft, and I have to refactor it, thanks to Bill this morning and yesterday. So what we will have to go is to go through the code that we have at the moment, see the things that we can improve, and go in that direction. The second thing that we would like to do is all this database backend with Django and things like that, well, get it out of the way and replace it with something also in Go. And we were a bit lost because there are a lot of frameworks here to do all these things, and maybe it's not even needed to have a framework for that, but well, we'll have to check it in that. I talked to Florian and he gave me a couple of nice points. In particular, something that I was looking for is to have the single sign-on and shibboleth authentication on the web servers. So if someone around here knows more about this and how to integrate it properly, I'll be happy to talk to that person. More things that we want to do to make the service, the load balance daemon, to be able to talk to it a bit more interactively. So instead of just reading the configuration file and someone having to change the configuration file and restarting the service, to be able to send it more things. So whenever we want a new alias or to delete it, to do the thing immediately. Also, that the slave and the master, they have a bit more of synchronization so that they can talk to each other, then without needing more things. And most of the things that we have done at the moment, they are quite generic. It's using DNS just because on the server we have something that will talk to the DNS to update it. In principle, we could use it also for any other thing where you have a list of hosts behind and you want to get the healthiest behind. So why not to have like a HA proxy backend instead of a DNS, something like that. And finally, the last point that I've put here is to create some alarms. We have the basic ones of when our service is running or when our service is not running and things like that. What we want is something that will tell also the user when the aliases that they have created, that they don't have all the nodes that they want, and if there's something that they could do about it. Oops. No, don't tell me that it goes back. So with this, I get to almost my last slide for today. What I have presented today here is an open source solution for load balancing. The code is there. It's going to change quite soon after this workshop to accommodate to all the things that we have learned here. And we are very happy with the parallelism that we get thanks to Go in this particular scenario. What we have is a list of aliases that we want to update, and we have set it up in such a way that we can distribute it by partitions and then having still a high availability with master-slave setup that will update all these aliases. The code is quite easy to deploy and maintain, and we have automated the whole process from the development until the deployment thanks to GitLab and Koji. And then we have also all the monitoring with the Logstars, Elasticsearch, and Kibana Slim. If you want to get in contact with us, this is the email. And before finishing, I want to put one of the quotes of someone who came to CERN, and I found it very, very nice. So magic is not happening at CERN. Magic is being explained at CERN. And if you want to help us explain the magic, please come to our website and apply for some of the jobs there. Thank you very much. And I'm happy to take questions.
Don't be shy. Your last chance. So. Oh, sorry.
Thank you. One question: how many people currently work in CERN and work with Go?
So for this particular project, we were 3 people working like 10% of our time, each of us.
Do you plan to use Go in next projects?
Let's see. I like the question, and what I've used the language. I like it a lot. Unfortunately, for myself, I don't have a lot of development, so I don't think I will do it myself. I will really encourage some of my colleagues to use it, though. So if some of my colleagues want to look for something else, I will very gladly help them and lead them in this direction. Because I've seen a lot of the things here that it makes the language quite powerful.
More questions? Okay, then. Thank you, Pablo.
Thanks.